Hi everybody, welcome to the Prelab video for Experiment 7. I'm Professor Jacob Stewart. I teach one of the lab sections, and I'm going to walk you through sort of the plan of attack for this experiment and what we're trying to learn. So the goal of this experiment is we are analyzing a weak acid, and we want to understand its equilibrium. And the way we're going to do this is via titration. Now, if we were actually doing this in lab, you would normally need to do two different sets of titrations to be able to do this. All of this is going to be provided to you as data, right? This is a virtual experiment. But the two parts we would need to do are, first, we would need to standardize our titrant. And this means we would prepare something that we know the concentration of. In this case, it would be KHP, potassium hydrogen phthalate. And that's going to react with sodium hydroxide, which is our titrant. And we have prepared our sodium hydroxide, but we don't know the exact concentration of it. And so we react it with a known amount of KHP. If we know the volume of the sodium hydroxide, we can standardize that. So you did this experiment previously. We have some data that you will be analyzing that was given to you in the lab report to figure out what is the exact concentration of the titrant. The key to remember here is that your moles of KHP are going to be equal to the moles of sodium hydroxide. And then once you know the sodium hydroxide plus the volume of the sodium hydroxide that it took to react with that much KHP, you can find the concentration from there, because our concentration is going to be equal to moles per liter, right? Okay, so that's the first part of the lab even if we were doing this in person, we wouldn't actually do this part. You would just be doing the calculation based on this. The second part is that we use the standardized titrant to react with our weak acid. And we don't know what this weak acid is. That is the goal of this experiment, is to figure out two things about it. We want to find out the identity of the acid, and we do this by finding the value of Ka, the acid dissociation constant, and we also want to know the concentration of the acid in the solution that we have. So there's two pieces of information we want to find at the end of this. Okay, so that's the overall sort of outline of the experiment and the goals. So let's talk a little bit about acid equilibria. So what Ka is, how it matters. So when we're talking about acids and bases, we can roughly put them into two categories. So we have strong acids and bases. These are things like hydrochloric acid, hydrobromic acid, sulfuric acid. And what characterizes these acids is that they completely dissociate in water. So if we look at HCl as an example, we can write the equilibrium of HCl in water. It's going to go, I'm not even going to write this as an equilibrium because it completely dissociates into protons and chloride ions. So whatever concentration of HCl we have, that is the concentration of hydrogen ions we'll have in solution. Sometimes you'll see this written this way, where we have H2O plus HCl, emphasizing the fact that the proton doesn't exist by itself in solution. It always associates with other water molecules, and so we form this hydronium ion H3O+, which is itself a simplification, but we'll just leave it at that. But the whole point here is that all of the HCl, when it goes into solution, it completely dissociates. And that's what makes something a strong acid. Same thing with strong base. A strong base is something like sodium hydroxide, which is the base we're going to be using in this experiment, potassium hydroxide. These as well completely dissociate into the constituent ions. So this is a strong base. We produce that much hydroxide ion directly. Okay, so that's pretty straightforward. But when we're thinking about weak acids and bases, that's the other category we have. And in this experiment in particular, we're going to be considering a weak acid. These do not completely dissociate. They donate protons, they produce protons in solution, but they do not completely dissociate in solution. So, for example, as mentioned in the experimental write-up, we can have something like acetic acid, HC2H3O2. Generally not used to seeing it written this way. But if we put this, and this is the acid that's in vinegar, right? So most vinegar is about 5% acetic acid, if I remember right. Anyway, this will do the same thing, but now you see I'm writing this as an equilibrium instead of as a one-way arrow. It will dissociate and produce hydrogen ions as well as acetate this ion here. But this dissociation is only partial. Only a little bit of the acetic acid will dissociate. Now the question is how much of it dissociates, and that depends on which particular weak acid we're considering. The way we keep track of this is we can, right, this is a chemical reaction. We can write an equilibrium constant for this reaction here. We give this equilibrium constant a special name. We call it Ka. This stands for the acid dissociation constant, because it is an equilibrium constant for the acid dissociating. And this is what we're trying to find about our unknown acid in this experiment. And so the equilibrium constant for this reaction, we can write the concentrations of the products on the top. And we can write the concentration of the reactants on the bottom. Now all these are aqueous, so we need them all concentrations in molarity. And there we go, that's our acid dissociation constant. And every weak acid has its own associated acid dissociation constant. The larger the value of Ka, for weak acids, Ka is always less than 1, but the closer it is to 1, the more the acid will dissociate, because that means the products are more favored. And the smaller the value of Ka, the less it's going to dissociate. So that's a way for us to gauge how weak or how strong an acid, how weak or strong a weak acid is. If it's strong enough, then it's just a strong acid, completely dissociates. And we're going to take advantage of this relationship to find, in our titration, the relationship between Ka and H+. So as we're doing a titration, what's going to be happening in our solution? So let's imagine we have, so I'm going to sort of draw a picture here. We have our burette here. So this is what's going to be happening. We'll have a beaker here. And so we'll have sodium hydroxide up here with a known concentration that we found from standardizing it. And then we'll have our weak acid in solution. And we'll also have our pH electrode. And this lets us measure the pH as we do over the course of this titration. So we're going to be adding sodium hydroxide to our weak acid. We'll call this weak acid HA. This is A standing for acid in general. And so that has that hydrogen on it that's going to dissociate. And as we add hydroxide, it's going to react with the HA. So an acid and a base are going to react with each other. We have an acid-base reaction that happens here. This one, again, is not an equilibrium. This is going to go to completion and will form water and the conjugate base, A-, of our weak acid. And so this is the reaction that's happening as we do the titration. And so what's happening as we add hydroxide is our HA, our weak acid in solution, is being converted into A-. Now there's a special point, and usually what we're interested in a titration is the point at which we have equal moles, or I should say equal stoichiometric ratio. In this case, it is a 1-to-1 reaction, but sometimes you can have a different stoichiometry. But in this case, it's equal moles of OH- and HA. And that's what we call the equivalence point. And this point, if we pay attention to the pH, or are measuring the pH of our solution, this is marked by a very drastic change in pH all of a sudden. So we'll go from an acidic solution to a basic solution very quickly as we hit that equivalence point, because all of our acid is used up and is being turned into a base. And then after that point, we're adding extra hydroxide to the solution, which will make the solution even more basic. All right, so if we sort of plot and we'll look at a plot of this in just a little bit, an actual plot. pH versus the volume of our titrant. And so in this case, the volume of our hydroxide. It'll start low because we have an acid, and then suddenly shoot up at the equivalence point. So this is the equivalence point that we're talking about here. What this lets us do is figure out, since we know the concentration of hydroxide, that if we know the volume that was added, we know the number of moles of hydroxide that was added, and that equals the moles of HA, which lets us get back to the concentration, which is what we were interested in the first place. One of the things. The other interesting point is halfway. We call a half equivalence point. Somewhere about here. We take the volume here of the equivalence point, call that VE, and 1/2 times VE is this half equivalence point. And what's special about this point is at that point we have equal amounts of HA. Half of our HA has become A minus. So the concentrations of these are equal to each other. Now if we go back to our Ka expression, Ka is equal to, and I'll write this in terms of our generic acid here, we'll have concentration of H plus, concentration of A minus, those are our products, and our reactant is HA. At this point, we're at the half equivalence point, so here we're talking about the half equivalence point, not the equivalence point. Our concentration of HA minus and HA are equal to each other by definition. And so in this relationship, these cancel out. And so what we can see is that the concentration of H plus is going to be directly related to Ka at this point. So we can write that Ka equals the concentration of H plus. Pretty neat. And what we're measuring with pH is the concentration of H plus. So if we express both of these in terms of P, they're P values where we take the negative log base 10 of this whole equation, this will become pKa is equal to pH. Using the definition of pH and pKa where pH is negative log base 10 of the concentration of H plus. Same thing for pKa. All right, so we have this half equivalence point allows us to directly determine the Ka value for our weak acid. And that's what we're after with this experiment. So how would we actually do this in lab? So I just wanted to show you a picture real quick of what this setup would look like, as well as looking at this plot again. Okay, so on the left here, I have a picture of how you might actually do this titration in lab. This is a little bit nicer setup than we have, but the basic idea is there. At the top here, this is our burette, and this is where our sodium hydroxide is in this experiment that's been standardized. So we know the concentration of it. And then again, down here, this is where weak acid is. And this blue thing over here on the side, we'll use green, this is our pH electrode. So pH electrode takes advantage of some electrochemical principles to convert a voltage that can be measured with the pH electrode into a concentration, into the pH. So there's a direct relationship between the voltage measured on this thing and the concentration of H plus, because there's a membrane in there that's sensitive to concentration of H plus. And so as we add the hydroxide, we keep track of the volume that was added, and we keep track of the pH that's measured, and that's how we, this turns into our data here, our titration curve. All right, and this is, again, is showing, this is a nicer plot, this is from your lab write-up, of showing the equivalence point and the half equivalence point in a specific example. So at the equivalence point, again, we see this very sharp change in pH. You'll see this in your data. And one way to determine this equivalence point is you can sort of draw a line along here, and you want to take the point that's right in the middle. Right, and so that's going to be, that volume there is the equivalence point. And then once we know that volume, we can just take half of that value, go over here, and then read off the x value. So in this example, for this acid, because the pH is about 4.3 at the half equivalence point, we can say the pKa is equal to 4.3, which means that Ka would be 10 to the negative 4.3. All right, so that's the basic idea of what we're doing in this lab. So I hope this video helps you understand the principles that are going on, and I hope you enjoy working through the analysis of the data that you'll be provided. I hope you have a wonderful day.